Welcome everyone. My name is Naci Simsek and I'm working in Ververica. Maybe some of you might not know, Ververica is the original creator of Apache Flink. And then I'm working there as a head of support, so we are helping our customers, clients with their Apache Flink use cases, as well as the Ververica's product problems and issues that they might face. And then, yeah, my talk is about giving you some, brief introduction about the streaming landscape. Of course, in the center it will be Apache Flink, and then we will make sense what the streaming is, which kind of use cases we are particularly focusing on with the streaming, and then we will wrap up with a Streamhouse architecture to our presentation. Yeah, this is a little bit of background about me. You can follow me from LinkedIn. Ask any question if you like. After the presentation, I will be definitely have much more time. We can discuss about streaming and everything you would like to have. So, yeah, why does streaming matter, right? There are four items that I just list here about why streaming matters. The first one is the freshness. Second one, data velocity. Everything is an event. And then competitiveness, right? While we would like to go for streaming, these four items is making sense, basically. Like we would like to have our data calculated, analyzed freshly. And then the data velocity is too much in nowadays. So instead of waiting for batch applications, we would like to analyze our data in a real-time fashion. And then, of course, everything is an event. We are working on the event, and then using the streaming most of the time, having a less latency, giving us a competitive edge for our use cases, which I will be touching on. When we are calling streaming, we are mostly comparing streaming with batch, right? What I would like to do here right now is not like a comparison, which is good, which is bad. We will definitely focusing on the use cases itself. Like, what is the use case? Which use case makes sense for batch and which use case makes sense for streaming? So, of course, we all know batch is historical analysis, stream processing is for real time. Stream processing is a little bit complex than the batch. We will definitely discuss on them later on. But the most what I would like to focus here is that even when I'm discussing with our customers, clients, we are trying to solve a problem, right? I mean, there is a problem to be solved, and then what we need to do is to ask a question which is aiming for that exactly the problem is. How fresh you would like your data to be analyzed, prepared, based on your use cases. So what we are focusing on when we are make sense of the streaming is that how fresh you would like your data is. So this is a key concept when making sense of a streaming over batch. How fresh you would like to have your data. So I will be touching three important use cases where the streaming makes sense. The first use cases are event-driven use cases. Like, we have some event-driven applications, right? For example, we are performing some credit card transactions, and we would like to identify the fraud cases. I mean, if we would like to analyze those events 1 day ago, 2 days ago, and catch some fraud actions, this catching fraud events will be helpful to who? I mean, no one. So customers would like those events, those actions to be catched in real time. So fraud detection, fraud alerts, is a perfect make sense of the streaming applications. Another one is, let's say, Formula 1 car, right? Formula 1 car is pushing the brake, and then the brake pedal is like heating up a lot, and then there should be an immediate action needs to be taken on this. We cannot take the action after the race. So this is a perfect streaming use cases. Another use case, we are watching football game. Football game is 1-1, and then the 18 minute, it's becoming 2-1. All the odds, all the ratings are immediately being changing. They're not changing tomorrow. So they need to be changed to keep you engaged to the game, to make more odds. So this is a streaming use case. These are all event-driven use cases, where the latency matters. The second use case, ETL CDC. You have RDBMS, and you have a web application, and then there are some products defined in your RDBMS, but you are running a search, right? You would like those RDBMS records to be immediately synced to your Elasticsearch database, for example. This is a perfect use case that you are synchronizing two databases in real time. So these are some ETL CDC cases that we can definitely discuss in detail. And then lastly, analytical use cases. You have a dashboard, real-time data. You don't want this dashboard to show you like data in 15-minute or hourly batches. You would like the data to be changed directly on your dashboard in real time. For example, you are doing some stock market trading or something like this. That dashboard needs to be backed with some streaming platform in the background. So the landscape, we are talking about streaming. We have different tools, technologies, techniques that we are applying in this landscape. These are platforms, libraries, frameworks, databases, engines, and architectures, which I will be touch some of them. So the first one is the streaming platform. Streaming platform is the backbone of every streaming architecture, right? We were having an architecture like this, like microservices are communicating between each other in a synchronous fashion. Then we think about, let's make this like a communication between the microservices async, and then we place an event streaming platform in the middle. So all the microservices with this event streaming use cases put all these events in the streaming platform in the middle, and then this opens the way of the world of streaming for any different use cases. Although these are right now focusing on only the storage of the events, they definitely open the world of processing those events as well. So when we talk about streaming platforms, what is coming into mind? It's Kafka, right? There are a bunch of others like Red Panda, Apache Pulsar. I will put a small question mark. We will come back to that question mark later on. And then these are all the abilities of all these event streaming platforms, right? They give us the throughput of like a low latency analysis of those events. They are durable, they are scalable, right? Distributed systems they are. Like they have, some of them, they have a huge ecosystem. Some of them is like cloud native, giving like multi-tenancy geo-replication out of the box. So this is what I write here is that Kafka, we are choosing Kafka for its ecosystem and community. It's a huge community, as you may know. Pulsar is just built up as a cloud native event streaming platform. It has multi-tenancy geo-replication, all these built in. And then Red Panda, we cannot see its name because of it's not that long, but it's simpler than Kafka. Kafka is a JVM-based event streaming platform. Red Panda is written in C++. So if your use case is really latency sensitive, you might go for that option as well. And these are some cloud vendor-based event streaming platform options like Amazon Kinesis, Google PubSub, and Azure Event Hub. Okay, right now events are sitting our event streaming platform. What will be the next action? We would like to read those events, right? Transform, aggregate, join, react on those events, like route, store in different architecture. So what will be the entity that we need right now? The entity is, of course, platforms are storing the data, and now we need a processor that does something with that event. We do not like only mention it as a processing engine or processor. There are a bunch of different entities which can be doing these processing actions, which are like embedded libraries. For example, Kafka Streams, standalone frameworks, Flink, Spark, Python libraries, execution engines, Arroyo, which is written in Rust. I think recently it's been sold to like one company already bought it. Yeah, exactly. Portability layers, you can use Beam to deploy a job with Spark and Flink. And then streaming databases, there are a bunch of database options around if you don't want to like play with the framework directly. Pipeline connector tools, and then some CDC ingestion tools. DBZoom is the most well-known one, Flink CDC. There are new options like Supermetal RT is now in the game for these CDC options as well. So you can see some of them a bit colored, so I will be touching a little bit detail on each of these processing entities. Before going to the processing entities, we have also query engines, like, they call it OLAP query engines. You would like to visualize your streaming, you can use different options. You can take the picture or get the slides later on, and if you need some tool to visualize the streaming data, you can definitely check them out. And then finally, we have lakehouse table formats. It's funny enough, we have well-known Iceberg, Delta Lake, Apache Hudi, but there's another option here, Apache Pymon. Pymon is a Flink table format, basically, which is ground-up built based on a streaming use case in mind. So you can definitely check that another table format option out. So let's start with the Kafka Streams. Kafka Streams is running on your Kafka cluster. You are not deploying another cluster entity. So you have your Kafka topic, partitions, and then each partition is connected to a streaming thread, which in that thread your streaming task runs. This option is having something like really been doing well. You don't have to deal with any infrastructure in this case. It's Kafka native. So if you are heavily using Kafka, you can rely on this kind of processing entity. It's exactly once providing within the Kafka ecosystem itself. If you have simple transformations, join, aggregations, stateful, stateless, both, you can definitely use Kafka Streams. Kafka Streams is a Java library, so you are writing a Java code as your streaming application, Kafka Streaming application. So this is the summary of how Kafka Streams work. And if you would like to go for that path, there are some, of course, things to consider. It's definitely a Kafka and JVM only. There's no SQL interface. Nowadays, many of the analysis people also would like to deal with the streaming use cases, so they would like a SQL interface to work on, so it doesn't provide that. If you have some custom watermarks, if you would like to apply some exactly one semantics between some other sources other than Kafka, this falls short. So again, if you have some non-Kafka sources, you would like SQL interface, complex event logic, some extra monitoring UI, some like huge state scale, or some back pressure handling, you may consider some other options. The second option is ksqlDB. When we are going towards writing some Java code, Java application of doing streaming, to make it something easier, we focus on handling these options with the SQL. And ksqlDB, one of the first contenders, one of the first tools which we are applying these options. So ksqlDB, other than the Kstreams, has its own cluster. You can see it has its own client that you can write your SQL query, and then that SQL query is performed under this ksqlDB cluster. It has its several engines, ksqlDB servers, and then of course you are doing the stream processing towards Kafka again. You are running right now your processing in SQL. Of course, it's a continuous query. You have your streams as your processing applications, and then tables are your Kafka topics, basically. You have windowing options, stream to table joins, materialized views. This is a first, let's say, try to going towards a streaming database. So when I will be talking about the streaming database, it will be a little bit making more sense. You have push-pull queries, and then of course it's Kafka native. And again, there are some points to consider going through that path. Again, it's a Kafka, then it's SQL only. If you would like to apply some low-level primitives of streaming, SQL may fall short in that kind of situations. Again, the consistency guarantees and everything within the Kafka ecosystem. No external exactly ones. If you would like to perform some horizontal scaling, it's bound to your Kafka partition count. And then maybe you know, ksqlDB was built in the company, which now the momentum of them is, of course, shifting towards to the Flink SQL as well. So you can also keep that in mind. And if your goal is to source beyond Kafka, large states, strong consistency guarantees, extended monitoring and observability, you can go for some other options. The third options are the streaming databases. So this is, for example, let me give a brief introduction about this. We would like to perform a query on Postgres database, right? And then let's imagine that that query will be a little bit analytical query. Of course, Postgres database is not an analytical database, but we are performing a query takes longer, and then we could think that let's make this query a materialized view. So not this will be calculated again and again and again. And then that materialized view, we view that data, but now we would like that data to be changed every incoming event that we have, because what we are working on is a data, and data is not stopping. It's like everything is still keep happening again and again. So streaming databases are working on, again, the materialized view concept, but this time, this materialized view is being updated for every single incoming event. So it's not like a Postgres kind of materialized view, but it's been updating itself with every incoming event through, like, for example, an event streaming platform like Kafka. So you have, again, a SQL interface for streaming databases. Streaming databases helps you deploy a processing application, plus having also a storage. That's why it's called database. You can combine several different entities within its processing capabilities. Right now you see it's ingesting events from Kafka, and then it's CDCing events from Postgres to, for example, join them in real time. It's PostgreSQL compatible, most of these streaming databases. Built-in state management is there, and then this is analysis-friendly systems. So how these systems basically work is that one of the most well-known streaming databases is Rising Wave. And then you can see events are coming from Kafka, and your materialized view is constantly being updated. No matter an analysis checks that data or not, system is running continuously and then updating that data. So you are burning your CPUs continuously, but maybe you need that data in like a fashion that you deploy some alarms, and then whenever this data reach to a certain point, you would like a real-time alarm to be generated. This is a way that you can apply these kind of use cases. But maybe you can see some shortcoming of these systems. They are all role-based because you are ingesting the event from Kafka. It's like a, let's say, a JSON event, like 20 fields. You are just ingesting it, and then you are ingesting in the next event. We are not talking about columns, right? There's another streaming database called TimePlus. They are achieving this column-based hybrid approach, so you can take a look how they perform this. So this database is keeping your materialized view up to date, plus your analysis can perform some analytical queries which will be column-based. So these are again SQL only, no complex event processing logic mostly on these entities. The memory consumption for these systems could be high. And if you would like to perform some ad hoc queries, you need to define its view first to be continuously calculated. It has some limited window functions, and then these systems are relatively newer, so it's still in an evolving architecture. The next item is the real-time OLAP query engines. So we were talking about the streaming database. Streaming database was continuously calculating our data. But in the real-time OLAP query engines, our focus is not the data at the first place itself, but the focus is right now the users. Users are performing the SQL queries to a real-time OLAP query engine, and then this engine is continuously ingesting the events, but these number of users can be highly concurrent. For example, you are using LinkedIn, right? And then imagine that millions of people are just refreshing LinkedIn page. How many people view my profile? This query, let's call it this query a real-time query. Of course, it's not like millisecond level latency, but you are seeing like a second level latency, how many people view your profile. And then millions of people is performing this kind of query. So these kind of queries are not backed by a streaming database, but an OLAP query engine. So this is like a billions of rows, and it's indexing those billions of rows. That's why many people can perform concurrent queries in these systems. Of course, these are applying some partition column pruning. You can definitely apply time series queries on these kind of entities. And this is how it looks. For example, ClickHouse, Apache Pinot, StarRux, all are well-known OLAP query engines. So you are ingesting your events from Kafka. These systems are calculating all these data in their columnar storage, and then any user would like to perform some real-time query, that systems are serving those queries in real time. Latency definitely depends on your data volume, but definitely this will be a way forward to have a multi-tenancy real-time data queries in your systems. So it's best definitely for ad hoc exploration, many users, many different questions. But also, these kind of systems are highly being used for application-specific health checks. For example, you are ingesting your application logs or events, all these information to these systems, and then perform some real-time actions whenever that application data shows there are some bottlenecks or problems on that application. So right now we are focusing on the stream processing frameworks. The first framework is Spark structured streaming. You know, we use Spark for our batch queries, but Spark is also used for the real-time queries. So what Spark is doing is a micro batch, not event per event analysis, but it's batching some of the events in its trigger and then perform some real-time queries on those batches. It may be helpful for some throughput sensitive cases, but if the cases is particularly latency sensitive, which mostly the real-time cases requires this, Spark structured streaming falls short. So trigger fires and then trigger fires again. All the time elapsed between these, just making your latency minimum. So latency is basically increased in this kind of situation. But you may know Spark right now has a real-time mode. You can deploy a Spark job with a real-time mode. It will perform the real-time entities like event by event, not like doing those micro batches, but real-time. But it is its own the beginning. So if you would like to perform some, for example, session windows, stream-to-stream joins, would like to apply exactly once guarantees, which many of the streaming applications definitely require. These kind of options are not right now supported by the Spark streaming real-time mode. You can check definitely the Spark open source documentation, but the Databricks runtime have some of those features already been provided. So for full feature set, I definitely would like you to go and check the Databricks documentation. But open source Spark 4.1 is running on a stateless operators only. So you are doing some basic transformations for your data. You are not performing any stateful computation or aggregations or calculations. Then we are moving towards Apache Flink. Apache Flink is ground up a stream processing framework. It's built up while the stream processing, event by event processing, low latency is kept in mind. So that's why when we are focusing on Apache Flink is, that's why it's the de facto standard of streaming applications. Flink is a library. It gives you an API to deploy your streaming application, but also it is runtime by itself. You are deploying a Flink cluster. So this is how Flink cluster looks. It has like a job manager, which is helping you to manage all your streaming application primitives, and then your task managers, the worker nodes, which is actually handling all these heavy lifting of aggregation calculation of your data. Library, Apache Flink is a well-known streaming engine, but when Apache Flink is first built, it was not providing all the APIs for the users. It was just focusing on the data stream API. It was like for event-driven applications, low-level APIs. For the software engineers, it was perfectly fine. They were just deploying all those low-level primitives and then their event-driven applications. But then the world moves towards to more real-time analytics, right? Then Flink deployed Table API and Flink SQL APIs, which some not like heavy Java users, but just only performing some SQL queries can also be able to deploy Flink applications, even can perform some event-driven use cases by just using Flink SQL, by using the complex event processing libraries, which is built in with the Flink SQL. And Table API is very likely with these data frames that we are using in Spark for batch. This is very similar approach. This is the deployment options of Flink. You can definitely deploy Flink on your local IDE. You can deploy your local cluster. If you still have some Hadoop clusters, you can deploy Flink on Yarn. Docker, of course, an option. But our customers, 99% of our customers are definitely deploying Flink on Kubernetes. There are different deployment options. You can deploy standalone, writing all the YAML files of the config map deployment, everything manually. You can use native Kubernetes mode. You are just deploying a job manager, and then job manager is handling to deploy all these worker nodes, task managers by itself. So users no need to deal with them as well. And then lastly, the Flink Kubernetes operator is a highly well-known tool that manages all your Flink application lifecycle within the Kubernetes clusters. So streaming, we are talking about streaming. I was just touching about 3 different use cases, but now I would like to mostly touch with the hard problems that we are focusing when we are dealing with the streamings. The first one is out of order event. In batch, we don't have that problem because we are ingesting all the data what we have into the framework, and then framework handles what we would like to do for that data. But streaming, there's no such way. In streaming, I cannot get all the data of the world into my platform. It's a continuous process. I just deploy my job, it's continuously running, and then I need to deal with all the data, what's happening there. And then many of the data is created out of order. So the stream processing engine needs to handle those out of order events, because we would like to mostly handle the events based on some timestamp ordering or some logic that we would like to have. The second is a late arriving data. Not every event is coming into our processing engine when it's created. Maybe the system which is storing there working slowly. So our engine needs to handle those late arriving data. For example, we are working on Windows. Let's say we have 30-second window, and then every 30 seconds we are calculating a data point. But the data point which needs to be in that 30 seconds came to our tool 31st second. So we already fired the window. 31st second, there's an event came which is supposed to be in that window, but it isn't for some reason. So the streaming engine, like streaming framework, needs to handle those late arrived events. So there are many different options that Apache Flink provides users for handling such cases. And then finally, the failure recovery. We are deploying a Spark job, fails, we run again. Fails, we fix something, run again. But in Flink, it's a long-running application. It just runs, and then you just let it run and perform what you would like to have. But it's definitely, there are some problems occur. It stops. So what is happening when the streaming application stops? It needs to roll back to where it left off, and then never use or never calculate the same event twice to keep the data calculation consistent. So the third option tells us the event streaming framework needs to handle these kind of failure recovery for its data resilience. So this is what we are, like all these three problems which is being addressed within the Apache Flink. That's why Flink already became a de facto standard of streaming. So these are like like Flink is working definitely on the event time of the events. Events have a timestamp, so you are definitely working on those timestamps. You can scale your Flink job to whatever scale it is by using horizontal pod auto scaling on the Kubernetes option. Exactly once everywhere. You have many source and sink systems that you are combining with Apache Flink, and then most of the systems either on source side or the sink side support exactly once, which is making your data consistency healthy. You can deploy batch jobs within Flink, so you don't need to deal with two different frameworks. Flink also performs batch queries, and then when the batch data finish, Flink is showing you a finished state. So it is working like Spark in that aspect. And then the ecosystem. Flink is a huge ecosystem which is having over 100 connectors that you can connect many of the systems that you have. So it basically solves all the hard problems of the streaming. So you maybe remember the question mark. There were like Kafka, Red Panda, Pulsar, and then I was just putting a question mark there, right? This question mark is basically focusing on a system called, before focusing on its name, let me just mention this. Streaming platforms are for event-driven workloads, right? We are storing the data in a row fashion. Like it's row-based. If you would like to query, for example, like random lookup within our Kafka topic, we cannot do. We need to go over all the events within the topic. But this is basically how it is. It's not a bad thing. This is how they build to handle these event storage. Like we have no primary key within the Kafka topics, like no projection pushdown, no time travels. So when we are moving towards from event-driven use cases to an analytical use cases, Kafka storing the data in the Kafka topic via Flink falls short. So we need another system where we store the events also, like calculate something, store the events, but those events can be handled in an analytical fashion. So this is called Apache Flux. Please check this out, see how it works. There are really nice videos in the community which is explained how the Flux works, what is just it aims, which particular problem is it trying to solve. But the particular problem it's trying to solve is that you have Kafka that you are ingesting the data with your Flink cluster and then storing into the Flux cluster then it opens you a new world to perform all these real-time OLAP query engine primitives, real-time databases primitives, which Flink was missing of before. We were always dealing with storing the data to a Kafka topic again, or some Elasticsearch for some search capability. But with Apache Flink, which is definitely running on Apache Arrow for in-memory columnar format, it's just opening the world of having both like a hot data that we would like to require millisecond latency, plus some cold data primitives. Like Apache Flink itself is tiering some historical data as a Pymon or even iceberg table format that you can also perform some historical analytical queries. You may remember the streaming database. I was just telling most of the streaming databases was row-based. One of the streaming databases aiming towards also making some column-based queries. But with Apache Flink, by combining with Flink, you are handling all these analytical use cases within one single platform. And by using Flink, not using Kafka for these analytical cases, are giving you much more ability to store your state in a less size, and then using less CPU for ingesting your data. Because when you are trying to ingest, for example, like changelog data from Kafka, Flink is deploying some extra operators to normalize those changelog events. But with Flink, you are not dealing with all these kinds of cases. So this is basically a Streamhouse architecture where we are placing Apache Flink in the center. Flink is working as a streaming storage, like events, tables, auto-tiering to our object store. And then Apache Pymon is for like the cold data for our historical queries. But what is important with Apache Pymon is that even we call it as a historical query, you can still perform like a minute level latency streaming queries. If your streaming query is not like requiring a millisecond level latency, but a minute is okay for you, you cannot do it easily with this one with Apache Spark. Hoodie maybe, but Pymon is basically ground up built for these kind of minute level latency streaming use cases as well. So this is how like the architecture, the data flow looks just as a reference. And then finally, with this talk, I would like to firstly just let in your minds these messages state, like we need to define our latency requirement. If hourly is fine, then don't do streaming primitives. Use for some batch engines. Definitely we have different layers, like we have platform layer, databases, OLAP query engines, and then framework. These are not the same. So I just try to explain you what is the difference between these layers and then where to use which one. Of course, push and pull differences is important. There are some fixed queries which the data is calculated and pushed directly in the materialized view, or we would like to pull the data whenever we would like to have to utilize that CPU usage. Definitely, I would like to recommend starting simple and then evolving systems over time. You can definitely look for libraries, engines, databases, and then go for a framework when your streaming use cases evolve. And then finally, when you need a full power of streaming, you will go for Apache Flink. And then for the Streamhouse use cases, we'll open you a whole new world for deploying streaming applications for all these three all these three different applications type that I just explained. With that said, thank you for all for listening to me. So you can go for this QR code for checking the Verwerker Cloud to deploy your first Flink job, explore how it's being deployed, how the Flink SQL is being used. And then with everything, thank you so much for listening.
Okay, thank you, Naci. Some question in the room.
Thank you. So, just an advertising for tomorrow. So I'm having a talk about one of these libraries. I mean, a new one, Kafka Streams, not Kafka Streams. It's a slightly different approach. And I think, I mean, implicitly you said that you should only use streaming if you have a real-time requirement, which is also what Confluent is always saying, but I don't believe that. I think I would change that completely. I would say that use streaming when you save money. And I think with all this stuff, with Fluss and so on, which is interesting, of course, but you won't save money. So you will still stick to this niche of real-time use cases, which are very little, right?
Your question is finished? When we are talking about money, it's a very sensitive topic. What is the use case? I mean, what is the use case? Saving money. Okay, saving money for which use case? What is the requirement? If we are in an Alibaba scale, Uber scale, or we are like a small company. I mean, there are many things needs to be discussed. That's why, for me, everything is a flexibility. Need to be flexible in these data world. This is my ideology.
Yeah, so my question is like with this Fluss-like integration, I'm not so familiar with it, but is this like, does this work like kind of parallel to the existing Flink state store with Forest or RocksDB? Is this like a replacement for that, or is it something kind of like separate entirely?
It's separate entirely. It's not replacing it. It's storing the data with its own cluster. But when we are focusing on ForceDB or some Flink, let's say RocksDB, this is all how Flink utilizes its state. But this one is more towards to the end user data, which they are making sense for their analytical use cases, for their real-time dashboards. So this is a little bit like in parallel with Kafka.
Okay, so to follow up on that, if I had like a stream aggregation job in Flink that was joining two streams and it needed to maintain its own state store, I would have that state, and if I pipe that state again to Fluss, it would be, I guess, duplicated, or I'd have to store more or less the same data twice.
This is, yes, but I mean, you are not querying your Flink state data, right?
Yeah, thank you.
So thank you for the presentation, it's very interesting. You mentioned some comparison between Spark Streaming and Flink, and you said that Flink is faster because it processes event by event, and Spark Streaming is micro-batching. Could you elaborate a little bit more about that? Because what I believe, if we do micro-batch, we process more events at once, that's why it gets faster. But if you process event by event, I mean, you have to serialize, deserialize event by event. This is one question. And the second, I know that there is some plugin for Spark for geospatial queries. Does Flink have something similar for geospatial queries? Thank you very much.
No problem. The first question is, I didn't say Flink is faster. I don't know if anybody remembers what I said. I said Flink is focusing on lower latency. Imagine you have one event and then you are combining the second event, third event, just to calculate those events, like combine. The first event is still sitting there. So how you see the latency is increased, right? I'm still waiting for some couple more events to make it micro-batch. Latency is increased. But if I just ingest this one single event, within a single-digit millisecond, I have a very low-level latency requirement. But if my requirement is like a throughput-sensitive, really fast data, of course, combining them, like batching them. Even Flink is doing those kind of batching, mini batches to improve the throughput with the back pressure kind of scenarios. So this is the key distinction. And then the second question, geospatial queries. I mean, if you could give some example, because
for example, if I have a geolocation, latitude and longitude, and I want to find this point into a polygon around the world.
When you are comparing these kind of queries with Spark and Flink, they are using the same logic, same primitives. What Spark does is that you are batching all the data and then it's performing the query within that batch. But what Flink does is that Flink, for example, have 1 hour windowing. Flink is batching all those 1 hour events into a batch and then perform the same geospatial query within that 1 hour batch. So there is no real distinction between these two in that manner. You can even perform the same queries within a batch fashion within the Flink itself. But I don't know if in Spark there are some separate special operators for geospatial queries. I've never heard of it. We are still writing our own Java code to perform, these.
In Spark there is the Sedona plugin that you plug into Spark and you do this geospatial queries because it's very heavy.
I see.
Heavier than a very complex join.
Understood.
But I also wonder if there is something similar.
I have never played with the geospatial data, so I don't know, but we can check it later. No problem.
Okay, thank you again, Naci.
No problem. Thank you.
So it's lunchtime, so we'll keep plenty of time for lunch, and see you again at 2 p.m. for the next sessions. Thank you.